Okay, so we are looking at how the data net is used in forward chaining and in something that we call as rule based expert systems. Incidentally, I have kind of jumped in both the textbooks that we are following. In my book, this all matter occurs in chapter 6, and in Brackman and Levesque it occurs in chapter 7 essentially. But since I started off by doing forward chaining, and this is a way of making forward chaining efficient, I am just doing this, and we are now taking slight diversion into focusing on the expert system aspect essentially. So, these are, as we said, forward chaining, and one of the terms which they use, which was quite impressive, was they call it as pattern directed inference systems. So, we will see either in this class or in the next class that essentially when we do this process of building this inference engine which does this match resolve execute cycle, we are essentially laying the foundation of implementing a programming language essentially. So, for example, ops 5 is a programming language, and whenever we talk about a different paradigm or different type of programming language, one of the questions we ask is how is control specified for execution essentially. And in these forward chaining expert systems, control is specified by matching patterns essentially. So, based on what patterns you can see in the data, the actions that will be done would be determined by that essentially. So, as I said in the last class, the rules are given by domain experts, and your task is to build a inference engine which does the match, resolve and execute cycle. So, once you have implemented an inference engine, or some people call it as a expert system shell essentially, then all that is left is to specify the rules which is given by the domain expert, and we will see maybe in the next class that we have to specify what is the strategy for conflict resolution, because at any given point there are many rules which are matching with many data, and it is really critical as to you choose the right rule to execute. So, how do you decide that high level strategy, we will look at a little bit later essentially. So, the thing about these rules is, if you go back to your first order logic, that they have variables in them, and we have seen the example in the last class. And they form the long term memory of the problem solver. So, they kind of do not change over the problem solving episode. Rules are something that you know essentially. So, as opposed to that, there is data or facts, they go into working memory. So, all this terminology was devised by Simon and Newell, who were one of the first people who worked with this area essentially, which is like a short term memory. In the sense that it stores only that information which is pertaining to the current problem that you are trying to solve essentially. Now, facts do not have variables. So, in some sense we have put an extra condition on what we started off by saying. We looked at the unification algorithm, and we said the unification algorithm is used to make two expressions or two formulas identical by substituting variables for some patterns or values. We allowed in general unification that both the inputs can have variables in them essentially. That is why our algorithm said if variable, if input 1 is a variable or if input 2 is a variable, you could do both things. But here we have a restriction. So, here we distinguish between the facts that rules have variables, because they store the kind of patterns that we are interested in, whereas data does not have any variables. It simply tells you what is true in the real world essentially. Now, obviously, it means you cannot have sentences like all men are mortal. This is not allowed essentially. Instead, if you want to reason with this piece of knowledge, you will move this knowledge to the long term memory essentially, because there is something that you believe in essentially, as opposed to saying that this is a statement in my first order logic. We also looked at examples which said, for example, that everything is on the table essentially, right. We said everything is on the table, and if Big Bertha is on something that will break, we are not able to do that sort of a thing here essentially. But how do we tackle something like this? So, we do not want to be able to not do these kind of these things. So, we move these kind of things into the set of rules. So, you may have a rule which let us say, to use the terminology of ops 5, I identify with P stands for production, and I give it a name. So, let us say this is called AMM, which stands for all men are mortal, and my rule is very simple. It says that if I have a pattern of this kind, then I can add, and the term they use is make, another pattern So, when we are talking about first order logic, we did not have the distinction between rules and facts essentially. Everything was a formula. The only rules that we talked about, they were rules like modus ponens, which were really meta rules. They were not really rules in the language. But in forward chaining expert systems, we are separating the rules from the facts. Rules have variables and rules go into the long term memory, whereas facts are simply factual statements about the real world that you are talking about essentially. And this rule basically says that if you see a pattern called X is a man, if you read it in English, then you can make a pattern saying that X is mortal essentially. So, observe that the right hand side is an action essentially. In first order logic, you would say for all X, man X implies mortal X essentially. But here you are saying that right hand side is an action, make or assert or add the statement that X is mortal essentially. So, we are gradually moving from logic towards a language which allows us to talk about actions essentially, and essentially such a language is basically a programming language, or language like C simply it contains only actions. It says say X is equal to 1, X is equal to 2, these are actions, right. But here we are putting actions on the right hand side of the rules, and the conditions for those actions to apply are the left hand side of the rule, which is why we call it a pattern directed inference system essentially. So, rules are of this kind. We will use the notation from ops 5. So, rule name and then pattern 1, pattern 2, some number of patterns, and followed by an arrow, followed by action 1, action 2, now each pattern can be thought of as a series of tests that you want to do on a token. Remember that the network gets token at the root, and a rule is interested in a certain pattern, and a rule is interested in only those tokens which satisfy the pattern it is specifying, and it is specifying the pattern as a series of tests, is a set of tests. This notion of set is important, because we are not interested, we are not constrained to say that do this first and do this first and do this first essentially. That is why we had said that the retail network can be constructed, there can be many different retail networks given a set of rules. You could test for some one property first, angle less than 90 first, and then you could check for color, or you could first check for color and then check for angle less than 90, but it does not really matter essentially, as long as both the tests are satisfied. You can do them in any order, and especially because the attributes are named, we have named attributes with values, you are simply saying test the value of an attribute to be something essentially. So, each pattern basically tests for some attribute conditions, and since the attributes are named, we do not have to specify it in any particular order essentially. So, what are the kind of tests that we can do? We can test for constants. So, you can sort of compare this with the unification algorithm essentially. Here in this case you are matching a pattern with a working memory element. In unification you were matching two formulas. There also we said that if there are two constants in the same place. So, for example, if two attributes have a constant as a value, then obviously the constant must be the same essentially. So, we can have constants as values, and if there are two constants they must be the same. If one of them is a constant and one of them is a variable, then obviously then the variable must have that constant built into that essentially. Then we are talking about patterns, remember the tests which are contained in the patterns. So, we can have variables inside essentially. So, we have already mentioned this, that variables when they occur they must have the same value. So, we had seen in the last or one of the earlier classes a rule which said that, for example, if we said that if student x is bright x, if you have two such patterns in a rule, then they both use the same variable name, this must be the same value. When we saw that in the previous example, that a cylinder rule was firing because there were 4 patterns in which there was a variable called x which matched the value b essentially. So, that is one thing. Then we can have expressions, arithmetic expressions. So, we can say for example, in one pattern there is a number called n. So, in some pattern, in some working memory element, this is a test we are doing, we are testing the attribute called number whose value is n, and the second pattern in the rule might say that there is a number, obviously a different number, but whose value is n plus 1 essentially. We can say that one pattern is looking, if one pattern matches let us say some data which has number 7 for example, then another pattern must match with data which has number 8 in it essentially. So, we can have expressions, we are talking about the tests that we can do in the rated net, and these tests are used to channel the working memory elements along the different directions. And finally, we can have logical tests. We have already seen, for example, we said that angle is less than 90. So, it is a logical condition that you can test for. So, you can use this kind of arithmetic tests like less than, or you can use and or and that kind of thing. You can have a sequence of anything that you can express as a condition in logic, you can put a test here. So, what are these tests? Each node in the rated network does some such test like this, and then based on the test or the answer to the test, it sends the token down different directions. Okay. Another important thing to observe is that each pattern is a partial description. Of matching working memory element. You do not have to specify the value or a test for every attribute in the working memory element. Supposing I have a record of students, I have, let us say I have one long record, it says that student name is Suresh, age is let us say 20, then physics marks are 40, then chemistry marks are 70 and so on and so forth. I could have a long record essentially. I do not have to specify a test for every such attribute. I may simply say if there is a student whose physics marks are more than 60, then do something essentially. So, in that sense patterns are partial descriptions of working memory elements that they are looking for essentially. You do not have to specify the whole thing completely essentially. So, that of course gives you a lot of power to do that essentially. And finally, we can have negative patterns. So, when we say negative patterns, we basically mean that there must be no working memory element matching the pattern. And that is also a very powerful mechanism essentially, but it allows you to say. So, in logical terms you are saying there does not exist something with some description essentially. So, I will illustrate this with a small example, and then you must maybe tell me what that example is doing. So, I will not write a name here, we will write the name after you give me some suggestion, but the rule is like this. We can specify this, something like this, that there is a student who is different from the first student that we are talking about essentially. So, whose name may be P, whatever P is, but it must not be N essentially. Observe that I have put a negation sign before this pattern, which means it is a negative pattern essentially. So, now we are talking about actions, the right hand side is actions. So far I have only said that there is an action called make, but we also have an action called delete, which we may say is remove. We also have an action called modify, and when we say modify 1, we basically mean the first pattern essentially. So, that 1 is the index of the pattern in the order in which they have been written essentially. Apart from this, of course, you can have other patterns, other actions which are not of interest to us right now. You could have something like print, or you could have something like halt, or some other things essentially, or read for example, or something. But so those are not of too much interest to us right now. Right now we are talking about this. So, when I say modify 1, I am saying modify the first, the working memory matching the first pattern. And I say change the rank of that working memory element to R, and maybe this, I do not remember the syntax, maybe this is not required, this bracket is not required. So, here is a rule essentially. Anyone wants to tell me what this rule is doing?
Sorts the students based on their marks. Then like arranges the students in the ranks.
Assigns ranks to them, assigns rank to them. So, starting with so if there is some working memory element which says that the next rank is so on. So, for example, if you are starting the whole process, you might create a working memory element which says that the next rank is 1 for example. And what is it saying now? It is saying, look at the first pattern. First pattern says that there is some student, we do not know what the name is, we just call him n or her n, whose marks are m, we do not know what the marks are, but the rank is 0, which means it is a convention between us that we have not yet assigned a rank to the student. And the next rank that I need to assign is R, and there is no student whose marks are more than, it should be m, right. So, I have written n here, it should actually be m. You can put brackets here if you want. There is no student who has got higher marks than the student that we are talking about, and who also does not have a rank. If all the 3 conditions are met, then modify the first student's record to say that his rank or her rank is R, and modify the second record which says that the next rank now available is R plus 1 essentially. So, you can see that if I have 100 students with their marks, then this single rule will do the task of assigning ranks to them one by one. Every time in every cycle it will match only one student. It may match more than one student, but then they will have the same mark, then we do not particularly care what rank you assign essentially. If you want to be very particular about that, then as a small exercise maybe you should write a rule where if they have the same marks, they must get the same rank essentially. So, maybe let me put that as an exercise here. What shall we call this rule? Some name we must give. So, let us say ranking, some name. So, modify ranking to give same ranks for same marks. So, in this class what we have done is we have looked at this language OPS5, we have not really stated it, but the language is OPS5 and how do we specify patterns, how do we specify rules, what are the kind of tests you can do in the left hand side of the rules, and we have looked at some of the actions make, remove, modify. If you see, this modify is equivalent to removing that working memory element and adding it again essentially. So, it is really a combination of remove plus create again essentially, but we for simplicity we have modify, because then we have to only specify which attribute you want to modify. So, when you say modify one attribute rank R, you do not have to specify much more. So, it is just a shortcut for doing that. So, essentially now you know what the scenario is in rule based systems or production systems. You have lots of data, you have many rules, then the rate algorithm basically allows you to match all the rules with all the data, and then you have a set of matching rules. Somehow you have to select one rule, execute it, whatever the changes you are, what are the changes you are making in the working memory, you are either adding new elements by make, or you are removing some elements by remove, or you are adding and removing and adding by modify. So, working memory is changing. Now, what the RetainNet will do is that only those modified tokens, in this example the 2 tokens that we have here for student and next, only these 2 would be fed to the network. These 2 tokens will go down the network again and it may activate some new rule. In fact, if there is one more student left in the database with no rank assigned, it will match that student, and that student, the next highest will get the next rank, then the next highest will get the next rank, and it will basically execute that many times. This particular example, it will match only once, or if they have the same marks, maybe more than one will match. But if there are many rules which are matching, if the conflict set is large, how do we decide which rule to fire next? So, that is the task of the resolve phase. Remember, we have match, then resolve, and then execute. So, in the next class that we meet, we will look at the resolve phase in a little bit more detail, and we will see how that is basically used to capture the problem solving strategy or an approach essentially. How do you select which is the next rule to execute? And we will also see that then in the process we have actually devised a programming language which works in a slightly different way essentially, where the control is in the hands of the inference engine or the algorithm essentially.